All right. Good afternoon. My name is Turner Bitton. I'm the Vice President here at the Jordan River Foundation. I want to welcome you to what we hope is the first in a series of events all about the Jordan River. A couple of years ago, the Jordan River Foundation launched our Friends of the Jordan River program, where we're asking local residents to support the Jordan River, to invest in everything from interpretive signage to maintaining and stewarding the Jordan River corridor. Today, we're excited to welcome Adam McKean from the Utah Geological Survey to give a presentation on the history, the geologic history of the Jordan River. So we're going very far back in time today to talk about this community asset. And with that, I'd like to turn it over to you, Adam.
Hi, Turner. Thanks for the invitation to present. My name's Adam McKean. I've worked with the Utah Geological Survey for about 10 years now, and I'm a geologic mapper in the Geologic Hazards program, and mostly working on new geologic maps. And I'm going to switch here and load my presentation. There you go. And Turner, do you see my presentation, not my speaker notes, hopefully?
Yep, it looks really good.
Okay, great. Then I'll get started. So today I'm going to talk about the path the Jordan River has followed over the last 12 to 13,000 years. From a geologist's perspective, this is pretty recent history. The image you see on the slide is a high-resolution digital elevation model created from aerial lidar data. The darker areas are lower and the lighter areas are higher. Overall, the change in elevation in this image is less than 30 feet. The Salt Lake City International Airport is just off this image to the right, and Great Salt Lake is just off the image to the left. We're also just north of Interstate 80. During my geologic mapping of this area with my co-author Mike Hilland, I saw this curious dark ribbon that has been cut into the relatively flat valley floor. After some research, we found that the previous geologists working in the area had described an ancient river which flowed west of the airport to Great Salt Lake. Building upon what they described with our geologic mapping, we pieced together this geologic story of the Jordan River and its deltas following the drying up of Lake Bonneville. Today, natural marshes are located in the depression and are known as Bailey's Lake. This afternoon, I'll briefly review the climate changes over the last 13,000 years and how it affected the Jordan River and Great Salt Lake. Then we will look at some of our new geologic mapping and how the path of the Jordan River changed over that time period. We'll also look at how earthquakes on the West Valley and Warren Springs Fault may have influenced the Jordan River. The figure on this slide is a simplified drawing we did on 1953 aerial imagery of the region to show how the Jordan River used to flow west and now flows north. During the talk, I will walk you through when we think these events occurred. First of all, since we are talking river and delta geology, I wanted to go over a few terms I will be using. The diagram on the left shows a river collecting, transporting, and depositing sediment from the mountains to the lake. If this diagram was Salt Lake Valley, the collecting system is the high gradient mountain streams eroding material from the Wasatch Range, followed by transportation of that sediment along bigger and bigger streams until it joins the Jordan River and flows down Salt Lake Valley towards Great Salt Lake, where the sediment is dispersed or deposited in deltas along the shore of Great Salt Lake. A few other terms you will need to know: when the river is in the low-lying flatlands, they tend to slow down and form large curves called meanders. Once the river enters the lake, the transported sediment settles out of the river and forms a delta. Deltas are located both above and below the water surface at the interface between the river and the lake, much like this photograph of the Mississippi River on the right, which is an example of a bird's foot delta. The white that you can see in the water is the sediment coming out of the river and being deposited in the Gulf of Mexico. The same process of collection, transportation, and deposition of sediments occurred on the Jordan River in the past and continues today. Some other terminology I will use today has to do with time. Geologists have divided the more than 4.5 billion years of Earth's existence into time periods with unusual names. Today, we're just going to be focused on the last two, as shown by the highlighted and enlarged areas with 2 black stars. The Holocene is the period we are now in, and it covers the last 11,700 years. Before that was the Pleistocene, which covers the last 11,700 years to about 2.5 million years ago. In the geologic record, these two represent pretty recent history. Just west of the Salt Lake City International Airport, seen on the right, figures the Bailey's Lake quadrangle. The quadrangle is the one I mapped with help from Mike Hilland about 8 years ago, following which I mapped many of the surrounding quadrangles, as seen on the figure on the left. The dashed red box in the left figure I will refer to later in the geologic map part of my presentation. Here's a photograph looking to the east towards Great Salt Lake. The photograph was taken from just east of the Salt Lake City International Airport from a helicopter. When I first started working in this field area, I didn't think anything very geologically interesting would come out of it. I was wrong, and will share with you what I learned. For example, the water channel you see in the photograph is the main channel for a Bird's Foot Delta, and it has a similar shape as the Mississippi River Delta we just saw, but it's much smaller. This Jordan River Delta likely formed between 2,000 and 4,000 years ago, when Great Salt Lake was deeper. Just as a side note, this is also the approximate location of our new state prison. Here's that same Bird's Foot Delta channel circled in red in the digital elevation model of the area that we made from lidar data from the Bailey's Lake quadrangle. Again, the darker grays and are lower elevation, and the lighter grays are higher elevation, with less than about 30 feet change over the entire image. As you may notice, there are other lake and river features in this image, like the ancient river meander channel of the Jordan River. I will introduce you to some of these other features as we go. Stuart Murchison also noticed this Bird's Foot Delta, as well as other meander channels north of the Gilbert shoreline, as part of his PhD work in the 1980s. Stuart also worked out a hydrograph for Great Salt Lake following the end of Pleistocene Lake Bonneville. Hydrographs are charts that show water elevation of lakes over time. For any geologists listening, this hydrograph used very few samples and could use some revision, just in case anyone is interested in tackling this research project. I know I would be more than happy to support you in that. The water level history is important as it determines the water depth for the deltas and the base level for the Jordan River. Great Salt Lake is a closed system, meaning there is no river taking water out of the Great Salt Lake. It is like a huge bathtub with no drain. So the wetter and cooler the climate, the deeper the lake will be. And conversely, the warmer and drier the climate, the shallower the lake will be. Climate was a main driver for the water level in Lake Bonneville and now Great Salt Lake. The lines on these two hydrographs represent the elevation of the lakes over time. The figure on the left shows the rise and fall of Lake Bonneville during the last major glacial event, or about 30 to 13,000 years ago, with elevation in meters on the left and time on the bottom of the figure. Lake Bonneville was about 1,000 feet deeper than our Great Salt Lake is today. About 15,000 years ago, the climate became warmer and drier, and eventually Lake Bonneville dried up. The figure on the right is a revised version of Stuart Murchison's hydrograph, with altitude in feet, not meters. The small blip at 11,000 years ago on the Bonneville diagram on the left is the Gilbert episode. Compare that to the zoomed in figure on the right, where the Gilbert episode is the deepest water event in the last 12,000 years. About 11,000 years ago, following the end of Lake Bonneville, during the cooler and wetter Younger Dryas, another lake occupied the basin and was about 45 feet deeper than Great Salt Lake's average elevation of 4,200 feet. We call this the Gilbert episode lake. Recent work by Jack Oviatt and others has shown that the Gilbert episode was shorter lived than what Murchison shows here. This was followed by a drier period called the altithermal, where Great Salt Lake may have completely dried up. Next is a cooler period called the late Holocene neoglacial, during which the Holocene high stand of Great Salt Lake formed to about 17 to 21 feet deeper than the average Great Salt Lake, followed by the cooler Little Ice Age and another rise in the lake. Again, this hydrograph is based on very few data points, but provides a basic approximation of the history of Great Salt Lake. Beginning in the 1840s, Great Salt Lake water elevation was scientifically recorded. These hydrographs report elevation in feet on the left and time in years on the bottom. On the figure on the left, you can clearly see the 1870s and 1980s historic high stands of Great Salt Lake. That's where the water level reaches its highest elevation. The lake then was deep. The lake during that time got to as deep as 4212, or 4,200 feet above sea level, or about 12 feet deeper than the historic average elevation for Great Salt Lake, which is about 4,200. If I rescale the blue image, the right image, that shows a record since 2008, and add a blue line that represents the historic average elevation, you can see the lake has been mostly below the average elevation for most of the last 20 years. To help me understand the source of gravel, sand, silt, and clay deposits I was mapping, and to help determine what elevation Great Salt Lake was at over time, I created this gradient shaded map of the northwest corner of Salt Lake Valley. To help visualize what you're seeing, everything below the color gradients would have been underwater at different times. I'll describe them from oldest to youngest. First in purple is the Gilbert shoreline elevation. In teal is the early Holocene high stand. In brown, the late Holocene high stand. In red, the historic high stand. And in blue on the chart on the left is the historic average elevation, which does not show on this figure because it's farther out on the lake shore. To test my models, I compared them to historic imagery. Here's a Landsat image from the historic high stand in 1987 for the southeast side of Great Salt Lake. When I compare this image to my models of lake elevation, I found there is more area covered by water in this image than my water model showed for that time period. This is likely due to shallow groundwater filling depressions near but not connected to the lake, and wind wave runup or areas where storm waves push the shoreline farther inland. With more areas covered with water than I modeled, that means that the models need to be taken with a grain of salt, but are still a reasonable representation. Just for comparison, the second image of the same location shows the lake area in September 2018 near its historic low. Much of the wet area north of the airport is wetlands, and the impounded water is for the waterfowl hunting and migratory bird refuges. So here it is again, the 1980s, 1987 water compared to our recent 1918 or 2018. I'm now going to walk you through what I found in our geologic mapping for the Jordan River. The image on the right shows the Granger and Taylorsville faults of the West Valley Fault Zone and the Warm Springs Fault on the Wasatch Fault Zone in black, with an aerial photograph beneath them, and the same modified hydrograph on the left as before. We'll start with the Gilbert episode lake and the Paleo-Jordan River and step through to the Jordan River today. About 11,000 years ago, during the wetter and cooler Younger Dryas, the Gilbert episode lake formed. A spit or gravel bar developed on the south side near Magna, seen here by the horizontal darker orange area. The spit developed near the lake's southern shore when the lake was deepest. As the lake retreated, a migratory Jordan River and small delta followed the retreating lake shore, as seen by the colored areas that trend to the northwest. These migratory channels are something that Jeff Keaton, Don Curry, and Susan Oleg mapped extensively in their West Valley Fault Zone study. Their paths are shown by the lines with arrows on the figure on the left. The mapping of the Jordan River is very similar to our mapping shown on the right. Next is the altithermal, or a period of mostly drier and warmer climatic conditions. During this time, the location of the Jordan River shifted to the north and flowed in a meandering channel to the west, underneath where the airport is now. To the northwest, it formed a large low-bait delta on the shore of a fluctuating Great Salt Lake. Water levels on the Great Salt Lake would have been between about 4217 and 4190 during this time. The low-bait delta would have been subaerially exposed or above the lake waterline when the lake elevation was below about 4212 feet elevation. During low water elevations, the Jordan River incised or cut down through the Lake Bonneville deposits, creating this incised meander we see and refer to today as Bailey's Lake. Next is the cooler and wetter Holocene High, where the water levels would have gotten as deep as 4221 feet. During this time, the Jordan River likely stayed in the same place and the low-bait delta would have continued to form. In addition, we think that this is when the Bird's Foot Delta, seen in blue, likely formed in deeper water. The Bird's Foot Delta could have represented the full river channel flow or just a splay of the main Jordan River. The Bird's Foot shape is likely due to it being deposited in relatively shallow water with less wave action when compared to the low-bait delta, which would have been exposed to more wave action on the shore of Great Salt Lake. Then the Jordan River shifted to the north and abandoned the western path, creating minor channels and a small delta. The river did not likely follow this path for long, as the channels and delta deposits are small and limited in size. The Jordan River then incised or cut down through that delta and established a floodplain along the current path of the Jordan River to where it enters Farmington Bay. In Farmington Bay, there is no clear delta deposit, so it has either been modified by the duck clubs and the Farmington Bay waterfowl management area, or the shift occurred relatively recent geologically speaking. This final step in the figure shows all the migratory paths of the Jordan River and the delta deposits together, and are color-coded by age. Essentially, the river migrated from south to north and west to east over about the last 11,000 years. The next question is, why did the river do this? Why did it not continue to empty into the southeast shore of Great Salt Lake instead of Farmington Bay like it does now? Earthquakes like the 2020 magna earthquake happened as the result of fault movement at depth. And if the fault movement is large enough, like a magnitude 6.5 or greater, you get offset of the ground's surface, which forms a scarp. We think the Jordan River shifted because of earthquakes on the West Valley Fault Zone and the Warm Springs Fault of the Wasatch Fault Zone. These faults are normal faults, meaning one side drops down and the other side goes up during an earthquake. The bar and balls on the black fault lines indicate which side goes down. Multiple large earthquakes on these faults lowered the surface of the ground between the faults over thousands of years to create a depression or trough that geologists call a graben, along which the river could flow north instead of west. The timing for the large earthquakes in thousands of years is shown on the left figure. The data for the West Valley Fault Zone is from 2 UGS fault trenches marked by red triangles on the figure on the right, where our geologists determined when the earthquakes occurred. From the Granger Fault trench site, we learned the most recent surface fault earthquake occurred about 5,500 years ago. Cross-cutting relationships indicate the Paleo-Jordan River was still flowing west here until sometime after 5,500 years ago. We know this because the 5,500-year-old earthquake would have formed a 3 or 4 foot scarp or step in the riverbed like it did to the north and south of the Bonneville deposits. North or south of the Jordan River in the Bonneville deposits. However, the river was still flowing west at that time and must have washed away the scarp that formed across the riverbed. We also dated some samples of ooids with help from Dave Tingey and Kevin Ray at BYU, seen by the yellow diamond. The ooids formed in Great Salt Lake between 6,000 and 7,500 years ago and were deposited onto the delta bar sometime after that. So we know the delta was active at least 6,000 to 7,000 years ago. At the Taylorsville Fault Trench site, a change in sedimentation from the river channel sands about 6,300 years ago to floodplain and marsh silts by about 4,900 years ago may correspond to the Jordan River shift from west flowing to north flowing. Additionally, the shift from west to north also likely would have occurred after the Bird's Foot Delta formed, or about 4,000 to 2,000 years ago. These lines of evidence place the shift from at least after 5,000 years ago to perhaps only a few thousand years ago. However, we do not yet have any direct geologic evidence to show when this shift, when exactly this shift occurred. One additional evidence of faulting impacting the Jordan River are some small lakes or sag ponds that formed on the hanging wall or downdrop side of all three faults. The red arrows on the figure on the right show where these lakes occurred, and they're represented by the darker tan color on the map. These faults created small depressions into which water collected. Most of these lakes and their evidence are now covered by development. It was through aerial photograph mapping on older aerial photographs from 1937, reviewing old topographic maps like this one on the left, and that shows the old Hot Springs Lake next to Beck Street, as well as older geologic maps and descriptions and photographs from historic records, that the presence of these sag ponds were correctly identified and preserved on our new geologic maps. In summary, we think that the large earthquakes may have contributed to changes in the flow path of the Jordan River. So we'll start here with the Lake Bonneville till about 13,000 years ago. Then we had the Gilbert episode delta and river forming, followed by the Paleo-Jordan River flowing west to Great Salt Lake, forming the Lowbait and Bird's Foot deltas. And you can see that WV5 is the earthquake about 5,000 years ago, or S4 on the Wasatch. And then following that, the Jordan River shifted north between 2,000 and 5,000 years ago and formed some small deltas, following which the Jordan River cut down again and formed a new river and delta that flowed into Farmington Bay. Or sorry, it didn't have a delta, but it cut through the old delta into Farmington Bay. Thank you. Just as a note, if you're interested in the geologic maps we discussed today, they can be found on our website, geology.utah.gov. I'm also more than happy to discuss the geology of this area with anyone that's interested.
Thank you, Adam. I'm going to go ahead just really quickly. If you've been watching online on Facebook and you'd like to join us for the live Q&A on Zoom, we've posted the link in the chat. Just one moment as we get get ourselves figured out, and then we will move over to the Q&A section. Adam, would you mind clicking stop sharing? And that'll take your presentation down. All right, thank you. First, I'm going to start here with the two folks that we have on Zoom. Scott or Edie, do you have questions that you would like to ask? And we have a couple of other folks joining, so we'll get to those questions as folks join.
I don't right now, but I find it really fascinating.
Adam, if you were to kind of summarize this into a key takeaway for folks, what is the most interesting thing, just really quickly as a takeaway, that you would like to leave people with?
I mean, this was an area that I didn't really think had much of a.
I wonder if there's one in Bruno.
Just a second. Okay.
So I think, this was an area I didn't think had much of a geologic story to tell. And from our mapping, we learned that there is quite a bit there and some pretty interesting geology. The Jordan River, this is just part of the Jordan River story. We only focused on the lower quarter of its path. My geologic mapping to the south of here shows interesting interactions and flow paths of the Jordan River over, since Lake Bonneville, where Little and Big Cottonwood and Mill Creek and some of those other creeks kind of flow off of the mountains down into the Jordan River. So it's just a small part of it. I think it's pretty amazing to see the power and influence that the earthquakes had on the, or at least we think the earthquakes had on the Jordan River. That Magna earthquake last year was a 5.7, so it wasn't a large enough earthquake to offset the ground surface. It may have tilted it a little bit, but just think of larger earthquakes than that over the last 12,000 years, creating a trough or a depression that then the Jordan River could flow through. I think that's pretty cool, and that it's all preserved for us to see out west of the airport is pretty interesting.
And you mentioned in your presentation that you were using aerial photographs from the 1930s, or is that the correct timeline?
Yeah, we have an entire set of stereo aerial photographs. So that's photographs that overlap just a little bit, enough that if you look through a stereoscope, you can see them in 3D. Kind of like those little toys we played with as kids, where you put the photograph in and look through, and you could see it kind of in 3D. So we have an entire set of those available for the public on our website in our aerial photograph collection. And for me, those are really valuable photos because they allow me as a geologist to see what the ground surface looked like before it was mostly developed. By the time you get past the 70s and 80s for much of Salt Lake Valley, the area has already been urbanized quite a bit. So those early photographs are super valuable, and we're really lucky to have them and have a complete set, which is, for me, is great.
Thank you. We've had a couple of people join us here on Zoom. For those of you that have joined us here on Zoom, if you want to ask questions, feel free to turn your camera on and just ask those directly. Sharon did ask if the first part of the presentation is going to be available. Yes, we're recording this, and we'll get it edited and make sure that you have access to that shortly after we're done. But were there other questions from folks that joined the Zoom? I don't see any. One other question that I had about the aerial photographs, were they taken by the UGS, or were they provided by a partner organization or someone out in the public?
Yeah, so those 1937 photos were part of a federal soil survey. The name of the survey would have changed over time. So it was either like a soil conservation service or one of those soil science organizations within the federal agency. And so that they were flown by plane with some pretty fancy high resolution cameras even for their day. And that type of work continued even till today. The surveys that we have today are the modern equivalent of that, at least the aerial photo surveys that are flown today are a continuation of that.
Thank you. My kind of last question, sorry, I had a whole bunch come up as you were presenting, but my last question is, as you're looking at this, were there any kind of takeaways for either emergency management or kind of stewardship of the river in modern day, based on what you learned during the course of your work?
Yeah, so from my geologic mapping in the other areas surrounding that area, kind of northern Salt Lake, I was really interested to find how frequently the Jordan River shifts its path. It's an active living feature. Its flow path is determined by physics and all the processes that go into water flow over the earth. And in a lot of places we've put dikes and berms in to control that flow path, but there's still some places where the river continues to shift and to migrate. And so I think anytime that we're developing or building or working along one of these streams or rivers or the lake, we have to be cognizant or aware that the Jordan River and the Great Salt Lake, we can try to control them, but we need to be aware that they are, they can change. The Great Salt Lake is a great example of this. Its water elevation has fluctuated about 30 feet over the last 160 years. And so, who knows when we might hit a wetter climate period again, and it decides to rise in water level, or not, it won't decide, but it will rise in water level. Or we could continue in the drought conditions that we see and are persistent in for the last 20 years. We could see an even greater shrinking and exposure of the Great Salt Lake lake floor, and that has its own implications, either one. But as far as flooding of the Great Salt Lake, there can be some minor fluctuations in it, but with the water level controlled at Jordan Narrows, there's not as big of concern there as there used to be, like when the white settlers first came to Great Salt Lake, or to the Salt Lake Valley. So, but I used to, when I worked in our office before COVID, I would walk along the Jordan River almost daily. And even during big rain events, you still can get local rises in the Jordan River elevation that can flood the flood path and areas that aren't protected by berms and dikes. So just something to be aware of as you work and live around the river.
Thank you. There was a comment in the chat, and Darren, I just want to see if you'd like to just ask it verbally, since you had kind of a multi-part question there.
Yeah, sure. Adam, how you doing?
Hey, Darren.
So, hey, I have some questions for you regarding the groundwater in that area. How much groundwater is discharging in the area, and is there any known seeps in the Jordan River in that area?
I didn't notice any seeps into the Jordan River, besides areas where the streams that had been enclosed in pipes were entering it. So that occurs in a couple of places. And I'm not a groundwater specialist, and so I'm not sure if there are other records of that. There is a groundwater study that you could find for the Northwest Salt Lake Valley on our website on geology.utah.gov. There are some natural groundwater seeps and springs where the East Bench Fault and the Nibley Park Fault are. So those faults are located east of the Jordan River. In Salt Lake, it's about 11 or 13th east. And where that occurs, there are natural springs there, but that's at least a couple of miles from the Jordan River. I can't think of any other natural springs along the Jordan River, and I don't remember seeing any on the topographic maps. As you get farther out towards the west of the International Airport and north of the International Airport, there are artesian springs. That's where they've drilled deep enough that they've hit water. For those that aren't familiar with it, there's wells that were dug that went deep enough that they hit pressurized groundwater. And so that flow path would allow the water to come to the surface. I don't know if those artesian wells still flow today, but there definitely are some out there west and north of the airport.
Okay,
Did that answer your question?
No, that's the thing. We're just doing some research on that, on stuff like that. So I just didn't know if you knew of any good places to go.
Yeah, just another one that comes to mind are the springs along the Wasatch Fault, there along Beck Street. I did some mapping there a few years ago, and a couple of those springs still are flowing. All but one of them, I think, are on private property, but those property owners have been pretty willing to let geologic groups out to see those and sample them. So if you contact me, I could get you some information on those, or at least I know the right folks to talk to.
Okay, thank you.
Yeah.
Are there any other questions from folks here on the Zoom?
I've got a question.
Yeah, go ahead.
Two questions actually, and I don't think they're even related to each other. The first question is, so I've done a little bit of research, not a ton, but a little bit on the Great Salt Lake's lowering levels since basically the 80s when I was born. Do you know if and maybe you mentioned this earlier, but do you know if the natural shifting of the Jordan River from the faults and stuff has contributed to the lowering of the level of the Great Salt Lake, or is that really more just the man-made damming up the feeding
Sure.
rivers?
Yeah, so the change in the flow path of the Jordan River most likely didn't have an impact on the lake elevation, because that same amount of water is still entering the lake. It's just going, instead of entering it on the southeast shore. So it's just say like the last 10,000 years where the Jordan River was flowing northwest under the airport to the southeast shore. Now the Jordan River is flowing north into Farmington Bay, and Farmington Bay is connected with the Great Salt Lake across both causeways. So the northern causeway that we access Antelope Island through, there's a bridge opening there. If the water is deep enough, it would also flow across the south causeway, which is disrupted or broken in a couple of places, eroded through. The south causeway you couldn't drive across it now, but in the early or the late 1980s, you could drive across it. It was actually the first access to Antelope Island. The Jordan River and other waters in the valley are also diverted from the Jordan River. So I think it's around like California Avenue, maybe. I don't remember the exact street, but the Jordan River splits into the Surplus Canal and into the Goggin Drain. And so some of the Jordan River still does enter the southeast shore of the Great Salt Lake. It actually flows, some of those canals from the airport dewatering area actually flow along the bottom of the Bailey's Lake or the old riverbed channel out to the Great Salt Lake. And so, the water is still making it into both the southeast shore and into Farmington Bay.
Okay. And the other question is, so along the Jordan River Parkway area, but in like the Taylorsville Murray area, about 4800 south, when that first went in, there was this boardwalk, which is still there. But what I recall from when I was young was that was always wetland, marshy area, and it hasn't been for a number of years. Is that has that been on purpose? That they've done that, or is there just not as much water flowing through the river anymore? Do you know what area I'm talking about?
I have a vague idea where you're talking about. There's a couple boardwalks in marshy areas.
Yeah, and it's right where I think
70th
Cottonwood enters in as well.
Yeah, I've been there. When I was there recently, it was pretty marshy, but I don't have anything to compare it against from the time you're referring to. The Jordan River level is controlled out of Utah, from Utah Valley down into Salt Lake, and it's some of that water is split off into a series of irrigation canals. And so I don't know the history of how much water has actually made it down the Jordan River and how much has been historically pulled off into the canals. I know it fluctuates. When we had was it 2011, Utah Lake levels were going up, and so there was debate whether how much water should be put down the Jordan River, and that gets at who you're going to flood. Is the residents in Utah Valley along Utah Lake going to have flooding on their property, or do you have some of that flooding along those that live along the Jordan River? Also, I believe, let's see, Mill Creek doesn't put out a lot of water. And it's pretty channelized from where it leaves Mill Creek Canyon until where it enters the Jordan River. And again, we could look up the history of Mill Creek in that area, or the Cottonwood Creeks, and see how much water has been coming down those. But again, it would change year to year. So I imagine during wet cycles like the 1980s, more water would be coming down those than in our recent past where it's been drier. So I don't have a direct answer for you, but that's kind of what I would imagine based on just what I know.
That makes sense. I know that they did make some changes to the banks and like riparian zone repair, something like that. But I just, as I was walking along there, I couldn't really imagine how nowadays water would have gotten into some of those areas.
Sure.
Because it would have to be so high that it would have been flooding.
Yeah, and the other thing to remember too is in some of those parts, some parts of that river, or that in some areas along the river in that location, the river has been straightened and made into like a channel with dikes on both sides, whereas other places it's allowed to spread out still. And so depending on where you are, humans have altered how the river flows, and some of those marshes have been removed and others have been left in place.
I see. Thank you.
Thanks, Eric, and thanks, Adam. Are there any other questions from folks here on the Zoom? I don't see any on Facebook, but if anyone here on Zoom has them, we can get to those. All right, well, I just want to thank everybody for joining us today. We are planning more events like this. If you have ideas for content or topics, or sounds like Eric and Darren are doing a lot of good work. If you are ever interested in presenting and talking about the river, we would love to collaborate with you on sharing information. So Adam, again, thank you for your time today. I just want to do one final plug for folks. The Jordan River Foundation, we're dedicated to preserving this natural resource throughout Salt Lake County and down into Utah County, and we'd love to have your involvement. Again, thanks, Adam, for your time. And unless there are any parting thoughts or comments, we'll go ahead and end the live stream.
Thanks, Turner, and thanks everybody for your questions. We appreciate it.
And Sharon, when the recording will be available. Sharon, I expect the recording to be available by Friday. So we'll get that to you. And if you just follow our social media, that's how we'll put it out. All right. Thanks, everybody. Take care.